Hello, this is Dr. Hanaa Assil, and we're talking about chromatography. And in this syllabus, the chromatography are different types. So we have paper chromatography, thin layer chromatography, which is TLC, high performance liquid chromatography, HPLC, and gas liquid chromatography or gas chromatography or GC. So we will be talking about all of this. So let's start with paper chromatography. In paper chromatography, what I have is I have a paper and I draw a baseline near the bottom of the paper in pencil so that the pencil does not affect any of the solvents that we're working with. And then we put a spot of the sample on that baseline. So there is a spot of the sample on the paper near the bottom of that paper. Now I'm going to put this paper into a beaker containing a solvent. Usually the solvent is water or ethanol or any other liquid, and we allow this solvent to move up the paper. So what we're doing is we're doing differential partition of my components or of my sample between a mobile phase and a stationary phase. Now, in paper chromatography, the mobile phase is the solvent in the beaker, which is usually water or ethanol or any other liquid. The stationary phase in this case is the chromatography paper, but this chromatography paper is actually water trapped between cellulose fibers of the paper, and the sample now goes up the paper and is separated into different components based on what? Based on different solubilities in the solvent. So the spot, in this case, the blue spot that goes up very high is a substance that is very soluble in the solvent. The spots that did not go up that high, green spot, yellow spot, or the light blue spot at the bottom, all of these did not go up very high. That means that there are components that are not very soluble in the solvent. So actually what we're doing is separation of the substances due to different solubility in the solvents. So this is called partition. The substances in the mixture go up depending on their solubilities. And we said the one that goes up very high is very soluble in the solvent. The one that does not go up is less soluble. Now, in paper chromatography, we can determine the different spots that appear. And for example, in here, the blue spot at the top is very soluble in the solvent in the mobile phase, and it went up very high, while the red spot is not very soluble in the solvent. I can calculate something called the RF value. Actually, RF stands for retardation factor. And this is unique for each substance in a certain solvent. So when I have spots, in order to identify that red spot in component 3, I can get its RF value. And to determine the RF value is the distance moved by the spot. So that means with a ruler, the distance between from the baseline, the line where we put the original spot, to the spot that we're trying to measure, that is the distance moved by the spot, divided by the distance moved by the solvent. Remember that the solvent went up the paper until that horizontal line at the top. This is where I mark that the solvent went up. So distance moved by spot divided by distance moved by solvent, that is the RF value of the spot, and it can be used to identify the spot. Remember that any spots that go up the same height are actually the same substance. So in this case, substance A and substance 1 are probably the same since they went up the same height, or they will have the same RF value. The RF values of the substance are an indication of how soluble they were in the solvent. So the one with RF value 0.4, this indicates that it did not go up to half the distance, less than half the distance. That means it is much less soluble in the solvent than that red spot at the top, which has an RF value of 0.8. So just looking at the RF values or looking at the spots, you can determine um, approximately what the RF value was. In some cases, we do chromatography of spots that are not colored. And you should know that amino acids or sugars are not colored. So in this case, if I'm doing the chromatography of amino acids or sugars, the spots do not appear until I spray with something called locating agent. For example, amino acids do not have a color. I have to spray them with a substance called ninhydrin in order for the spots to show. So when we do chromatography of amino acids, at the beginning, I cannot see anything. And then once I finish the chromatography, I can then allow the paper to dry, spray with ninhydrin in this case, because these are amino acids. If we're talking about another substance, we will spray with something else, but in general, these are called locating agents. So I spray with the suitable locating agent, leave the paper to dry. I will start to see the spots appearing in their original positions. So the spraying of a locating agent allows the spots to have color to make it visible. This is a question about paper chromatography. He says a spot caused by amino acid has moved 42 millimeters from the baseline. So he's telling me that the distance moved by the spot is 42 millimeters. Now the RF value of the amino acids under these conditions is 0.62. So he's telling me the RF value of it is supposed to be 0.62. So what is the distance moved by the solvent? So in this case, we know that the RF value is distance moved by spot over distance moved by solvent. He already gives me the distance moved by the spot, and he wants the distance moved by the solvent. So I divide that by the RF value, and this is my answer. Okay, thin layer chromatography. This is called TLC, or referred to as TLC. In TLC, the stationary phase in this case is a solid. So this is basically very similar to paper chromatography, except that instead of paper, I have a glass slide and I put a solid like alumina or silica on the surface. We add some water to it, make it into a slurry, spread it on the glass slide, leave it to dry or dry it in an oven. And then we use it in chromatography in a very similar way to paper chromatography. I draw a baseline in pencil near the bottom of the glass slide. I put a spot of the sample that I want to analyze. I put this glass slide into a beaker containing a solvent like water or ethanol and allow that to move up the glass slide or the solid phase on the glass slide. And in this case, the separation of the mixture depends on the differential adsorption of the components onto the solid phase. So the solid phase is polar. If my substances have polar components, the polar components will be adsorbed very strongly. So they will move up very slowly with the solvent. If the components are less polar, then they are not adsorbed very strongly to the alumina or the silica, and they will move up with the solvent. So remember that the one that moves up further in this case is the one that is least polar. So it is based on adsorption. Adsorption is the separation of substances due to different attraction between the compounds and the stationary phase relative to their solubility in the solvent. So the stationary phase is a layer of silica on the glass, and the separation of my substances depends on how strongly the components are attracted to this stationary phase relative to their solubility in the solvent. So the one that is more soluble in the solvent and less strongly adsorbed on the stationary phase will move up further than something that is strongly adsorbed onto the silica. So a mixture of organic compounds was analyzed using thin layer chromatography. The RF value was 0.92 for one of the components in the mixture. What can be deduced about the attractions between that component and the stationary phase and the mobile phase? Now, if he tells me that the RF value was 0.92, that means my spot went up very far on the chromatography. So in this case, if the spot goes up very far, that means that the attraction between it and the stationary phase is not that strong. So the solvent took it up very high, and the attraction between it and the solvent is much stronger than the attraction between it and the stationary phase. Here the question says a diagram of a thin layer chromatogram of substance Y is shown. What is the RF value of substance Y? Well, if this is a question paper in front of us, we can just use a ruler to measure the distance from baseline to Y divided by from baseline to solvent front. But even without doing a calculation, a spot in that position is a spot that has gone far up on the paper, more than half the distance further up. So just looking at it, you can guess that the RF value of that spot would be about 0.75. Remember, RF value has to be less than 1. So your option D that says RF value 1.33, RF value can never be 1.33. If we say 0.25, 0.25 means that the spot went up only about a quarter of the distance. So this doesn't apply to ours. 0.6, if we say the RF value is 0.6, that means the spot went up just a little bit after half the distance. No, this is further up after half the distance, so the RF value would be about 0.75. Here the question says a chemist synthesizing a substance called ethyl 3-oxobutanoate looked for its presence in the reaction mixture using thin layer chromatography. The solvent used was a mixture of ethoxyethane, which is polar, and hexane. So he's saying he's using a polar solvent. Under these conditions, the RF value is 0.45. First, complete the diagram showing a chromatogram for this substance. If he says that the RF value is 0.45, where do you think the spot is? You should put a place where he says the RF value is 0.45. You should put a place where there is a baseline and the solvent front, and RF value of 0.45 means the spot is a little bit less than half the distance, so it will be somewhere in that region. Suggests why the RF value for this substance is significantly lower than 0.45 when just hexane is used. At the beginning he said he used what? He used a mixture of ethoxyethane, which is polar, and hexane. Remember, hexane is not polar. Hexane is a non-polar substance. So he's saying if I use only hexane as solvent, the RF value is very low. What does that tell you? That tells you that our substance is polar. So if you put it in a polar solvent like ethoxyethane, it goes up. But if you put hexane, hexane is less polar, so it is less soluble in hexane, which is non-polar, than in the polar ethoxyethane. Remember, similar substances are attracted to each other. Polar is attracted to polar, non-polar will be attracted to non-polar. The other type of chromatography is HPLC. HPLC is high performance liquid chromatography. Now, the difference here is we have a column of chromatography, and the stationary phase is a non-volatile liquid. Remember that in paper chromatography, my stationary phase was a chromatography paper. In thin layer chromatography, my stationary phase was the silica on my glass plate. But in HPLC, the stationary phase is a non-volatile liquid, so it's a liquid, such as a long chain hydrocarbon liquid on a solid support. We attach it to a solid support, but that is my stationary phase. And the mobile phase is then a polar solvent. So what we have is a solid support like silica attached to our stationary phase, which is the non-volatile liquid. And then we have a polar solvent going through the column. So what happens is the mobile phase, which is the polar solvent, goes under pressure through the densely packed column, and I have a detector at the end recording the retention time of each substance. Retention time is the time it takes for the component to pass through the column from the point of injection to the detector. So as we go through the column, the time taken for each substance to come out on the other side, that is our retention time. Remember, the more polar components in the mixture will be more soluble in the polar solvent, so they will go out very quickly. A non-polar component will not be soluble in the polar solvent, so it will go out much slowly, so it will take longer retention time. So if we have this recorded graph, the retention time for each substance is recorded. The one that comes out first, which is substance 1, took less time to come out of the column. So that means less retention time. That means it went through very quickly, and that means it is more polar since it dissolved very quickly in the solvent and was removed quickly. The other one, which is taking a longer time to come out, such as substance 3, that is less polar because it is less soluble in the polar solvent. So he's saying here two polar compounds are separated using HPLC. The retention times are not affected by what? The pressure used? Yes, of course. The more pressure I use, the shorter time it takes to go through the column. Particle size of the stationary phase? Yes, this will affect how fast a substance goes through the column. Polarity of the stationary phase? Yes, of course. We said if it is more polar, then the substance will go faster or slower depending on what kind of compound it's going through. But the concentration of the compounds will not affect how fast it goes through the column. In HPLC, what is the mobile phase and what is the stationary phase? Again, we said in high performance liquid chromatography, the mobile phase is a liquid, the stationary phase is a solid. In separation using high performance liquid chromatography, the stationary phase was polar, mobile phase was non-polar. Which compound would take the most time to travel? The most time to travel means it will be attached to the stationary phase and it doesn't want to go through the mobile phase. That means I want something that is polar. Which one is most polar here? The 1-chloropentane will be most attached to the stationary phase and it will go through the column very slowly, so it will take the most time. A high-performance liquid chromatography system used a column with a non-polar stationary phase and a solvent of methanol and water. A mixture of octane, octanol, octanol is an aldehyde, octanol, an alcohol, was placed into the column. What is the order of retention times? We look again. He's saying the column has non-polar stationary phase and a polar solvent. So the one that takes shortest retention time would be the one that is most polar. The one that will go very quickly is the one that is most polar. So octanol will take a shortest time while octane takes the longest time. A mixture of 4 substances was separated using HPLC. The separation was carried out using polar stationary phase, non-polar mobile. Non-polar mobile means the mobile phase. That means the one that goes through faster is the one that is non-polar. So which of the 4 substances is likely to be the least polar? That would be the one that went through very quickly, shorter time. So that is W. In high-performance liquid chromatography, which of these factors does not affect the time taken for a component to pass through the column? Okay, that's very similar to the other one, but here we have different choices. He's saying which of these factors does not affect. So the type of detector, will it make a difference with me what type of detector I'm using to affect whether the substance goes through the column fast or slow? No, of course not. So the one that will not affect the time is the type of the detector. All the other things would affect how fast the component goes through the column. Okay, the last type of chromatography is gas chromatography, or sometimes it is referred to as gas liquid chromatography. This we use to identify organic compounds that have low boiling points, very volatile substances that can change into gases very quickly. So my components here have to be in the gaseous state. It is similar to HPLC, but the gaseous substance enters the column contains the stationary phase, the sample moves through using an inert carrier gas. So here we don't have a solvent, we have an inert carrier gas. This could be hydrogen or helium or nitrogen or any unreactive gas or inert gas. So in gas chromatography, our sample is in the form of a gas and the column is stationary, but the substance is moved through using an inert gas, not a solvent. So the different components take different times to move through the column, so they have different retention times, and I can use the retention times to identify my substances, comparing them to the retention times for known compounds. The area under the peak in the chromatogram is also proportional to the amount of each compound in the sample. So if I have a certain sample and I analyze it, I can tell whether it has more of component of the first component or more of the second component and so on, depending on the area under the peak. So the area under the peak will tell you the proportion of the amount of each compound, and the number of peaks will tell us the number of components in the sample. So the percentage of a substance is the area of the peak over the sum of all the areas of all the peaks times 100. In gas chromatography, a gas containing a mixture is passed over a liquid stationary phase. The main reason a mixture is separated into its components is because they have different, we said in gas chromatography, the components are separated because they have different forces of attraction to the liquid. We're not measuring their boiling temperatures or relative molecular masses or volatilities. We are measuring how strongly they are attracted to the liquid. In gas chromatography, which of these would be the most suitable carrier gas? Remember, we said the carrier gas has to be inert. So in this case, the argon would be the most suitable. In gas chromatography, the time taken for a substance to travel through the column, remember, in all of these chromatography, the time taken for a substance to travel through the column, in whether we're talking about GC or we're talking about HPLC, this is called retention time. Which of the following statements about gas chromatography is true? Okay, let's see. The first choice says it is only carried out at room temperature. No, that's not right, because the sample has to be vaporized. We need our sample as a gas. So we don't do this at room temperature. It can be used for samples which decompose when they're vaporized. No, I want to analyze the sample as a vapor. So if it decomposes, then I cannot use this to analyze it. It can be used for non-volatile substances. No, it has to be volatile because I need it to be a vapor or a gas. So it can be used to measure the amount of each component in a mixture. Yes, we said from the relative area under the peaks, I can tell the relative amounts of each component. A component of a mixture will move more quickly through a gas chromatography column if it has what? What would make my component move more quickly through a gas chromatography column? If it has lower adsorption to the stationary phase. Remember, if it is strongly adsorbed to the stationary phase, then it won't move. It will not move through the column very quickly. If it goes through the column very quickly, that means it has lower adsorption to the stationary phase. In gas chromatography, which one of the following would increase the retention time for an alcohol? So which of these would make an alcohol go more slowly through a gas chromatography column? Out of all these, increasing the polarity of the stationary phase. Remember that an alcohol is polar. So if the stationary phase is very polar, then the alcohol will be more strongly attracted to it and it would go through slowly. So it will take more time, or its retention time would increase. Okay, that is the end of this video. I hope you found it useful. Thank you for listening.